So before we take up the problem, I would like to show the corresponding analogy from a mechanical system, and the system will contain one mass hanging down through one spring in the vertical direction, and we will first see what happens there, and that will give us a good intuition, a good feeling of what actually goes on inside RLC circuit. Because in RLC circuit, we cannot see the quantities of interest, which are voltage and current. However, we can clearly see things happening in any mechanical system. That means motion and other things. So first I would like to show that video from YouTube, and then we can proceed to solve problems on RLC circuit. So here you can see that we have mass here consisting of two separate masses, and they are hanging down with the help of a spring. And when this mass is released, of course, there is stretching in the spring, and then mass starts falling down, and then again it is pulled back by the spring. And this phenomena usually goes on for a certain duration determined by few factors, for example, mass and the surrounding medium. So this is an example of a mechanical system where what is called system oscillates. That means there are two forms of energy in the system, mechanical energy and kinetic energy. And kinetic energy in the form of motion of the mass, and potential energy will be in the form of stretching of the spring, and the energy keeps on getting converted from one form to another. And because of surrounding medium around the mass, which will be typically air, but it could be fluid also, or liquid, for example, water. So because of that motion of this mass inside that fluid, there will be dissipation of the energy of this mass spring system, and it will gradually lose the total energy, and ultimately it will come to a standstill. So if the system is perfectly lossless, that means there is no viscosity in the fluid surrounding this mass, then the system will keep on oscillating. That means moving from completely stationary to completely motion state, and energy will keep on changing from completely mechanical form, potential form, to completely kinetic form. So here some of the terms have also been mentioned, but here note down that they will talk about a term called beta, which we will be calling as alpha.
The loss of energy in an oscillator is called damping. In this video, we will be specifically focusing on damping in a spring and mass system. Damping can occur within the spring due to energy loss from internal stress, and as a result of external drag from air or water. The damping in an oscillator can be described in four ways: undamped, underdamped, critically damped, and overdamped. In order to analyze these categories, we can use the experimental values beta and omega. Omega, the angular frequency, is equal to 2 pi over the oscillatory period. 2 beta is equal to B over M, where B is the decay constant and M is the mass of the system. The decay constant is found by fitting the peaks of oscillation to an exponential curve. If beta is 0, the system is undamped. Perfect undamped motion is impossible to achieve with a spring and mass system in the real world. Over a short period of time, however, the decay from air friction is negligible enough that a spring and mass in air can be representative of an undamped oscillator.
So this undamped condition will correspond to scenario when resistor value is 0. That means we have only inductor or capacitor in the circuit. And as you could have seen that we will always have displacement of same amount and changing with time as a sinusoid function. And this phenomena will keep on going forever. And here you can see that there is air inside this beaker, and 400 gram mass is hanging down from the spring. So this is one extreme of the situation, ideal situation, and this situation is typically labeled as oscillation or resonance also. And it was pointed out that there are 4 states, but typically we talk about the 3 states. So the 4th state, which was undamped, is the extreme case of underdamped scenario.
The decay from air friction is negligible enough that a spring end mass in air can be representative of an undamped oscillator. If beta is less than omega, this.
So in this case, now beaker is filled with water. So this mass will experience lot of resistance while it moves in any direction, whether in vertically downward direction or vertically upward direction. And because of that, it will keep on losing the energy, and the energy gets transferred to the surrounding medium, in this case water, and that will ultimately manifest as heat inside the water. But since the amount of energy involved in these experiments is very less, so one can never experience a rise in the temperature of the water manually. But as you can see, the displacement of movement of this mass progressively decays, and it will ultimately come to standstill.
System is underdamped. In an underdamped system, the amplitude of each oscillation gradually decreases until the amplitude reaches 0.
So extreme case of this was undamped case.
If beta is greater than omega,
so now we have another fluid which is a lot more viscous, very thick. That means it offers a lot more resistance to any object which is moving through it. So because of this, you can see that the mass very quickly comes to standstill. That means it very quickly loses all of its energy to the surrounding liquid or fluid.
System is overdamped. In overdamped systems, the system returns to equilibrium without ever oscillating. If beta is equal to omega, the system is.
So another extreme case of this overdamped is, that means when beta is equal to omega, for our case it is going to be alpha is equal to omega. So in that case also the system moves and comes to standstill, but it achieves that state of stability in the shortest possible duration compared with any other overdamped scenario.
Critically damped. For critically damped systems, the system returns to equilibrium without oscillating as quickly as possible. This is similar to overdamped oscillatory motion, but it returns to equilibrium more swiftly.
Here also you can see that we have a mass connected to a spring which is stretched. So initially there is a certain amount of energy in the system, and it is in the form of potential energy in the spring. And when the system is released, spring pulls the mass, and spring undergoes compression, and there is a motion or the kinetic energy in the mass, and ultimately spring gets compressed. That means the kinetic energy finally gets converted again into potential energy, and this phenomena keeps on going back and forth until system comes to a standstill because of the friction between the mass and the surface. So here also we have two energy undergoing conversion from one form to another form. So in this case also, friction is always opposite to the direction of motion, like the case of vertical system. So here also on the right hand side, you can see that bar has become a height of almost 0. That means energy has been lost, and it will manifest as heat in the mass or on the surface on which the mass is sliding. So in such system, it is important to know beforehand that when the system is released to its own, how quickly it will come to standstill, and after how many, you can say, back and forth motion, or loosely speaking, how many oscillations. Now we are going to take up problems from RLC circuit. So I will show you the problem sheet. So here you can see that we have a circuit where we have one capacitor of value 1 by 27 farad, and it is in series with an inductor of value 3 Henry, and then there are few resistors around it, and finally a 12 volt DC supply which was connected to the circuit from, say, t is equal to infinity up to t is equal to 0. And then at t is equal to 0 moment, the switch is open so that this 24 volt supply gets separated from this RLC circuit on the right hand side. And then of course our objective is going to be find out what will be the voltage across capacitor for t greater than 0. So this is the problem we will have to solve. But I would like to point out here that this scenario, although looks a bit more complicated, in simple form will be typically consisting of one capacitor, one inductor, and one resistor, either in series connection or all of these three in parallel connection. So whatever may be the connection, series or parallel, uh, they will always lead to second order differential equation, and this is uh, electrical analog or counterpart of the mass spring system. So here also the energy exists in two different forms. For example, it will exist in this case in the form of electric field or charge on the capacitor. And once the switch is opened, we will see that the capacitor will start losing charge. That means losing the voltage or losing the energy in the form of electric field inside it. And there will be resulting current which will flow through the inductor that will result in magnetic flux, or in other words, you can see that energy in the form of magnetic field. So here in this system, energy from the initially in the form of electric field stored in the capacitor will start getting converting into the energy in the form of magnetic field in the inductor. And then finally the energy, complete energy transfer will take place in the form of magnetic field inside the inductor. The net charge or the net electric field in the capacitor is going to be 0. So you can say that the initial potential energy has got converted to 0, and in the form of kinetic energy. So now we have only kinetic energy, and then that charge flow of the current will then start putting charge on the plate in the reverse direction. That means bottom plate will start becoming positive, upper plate will become negative. So the energy in the form of magnetic field will start getting converted into the energy in the form of electric field inside the capacitor, and ultimately there will be a fully charged capacitor and a zero current or zero magnetic field in the inductor. So this phenomena keeps on going on, electric field to magnetic field, magnetic to electric field conversion. And because the current flows through resistor, in this case we will see it will flow through all of these resistors, 15, 25, 6 ohm and 60 ohm. So resistor converts energy into heat. So system starts losing the energy, and it will finally get completely deprived of the initial energy which was stored in the capacitor. So now here also question arises that how soon the voltage across capacitor will come to zero forever, and whether it will come in gradually or it will come to zero after a number of what is called oscillation or back and forth conversion between positive and negative voltage. So now I think you have some idea that what actually happens inside RLC circuit, and what is the meaning of overdamped, critically damped, underdamped, and as one of the video pointed out, undamped case. That means purely oscillatory case. So now you can try to solve this problem. That means try to find out the expression for voltage across capacitor. So what we have to do is first, of course, we have to find out what is the initial voltage across the capacitor, because as you can see that when switch is open, the 24-volt source gets isolated from the this RLC circuit. So this scenario becomes a source-free RLC circuit scenario. So in that scenario, we first need to find out what is some initial voltage, and then we need to find out whether the scenario is critically damped, underdamped, or overdamped case. Once we find out which of these three scenario is actually for the given circuit, we can write the voltage across the capacitor using the standard form. So here you can see the solution. When switch is open, we have a resistor 60 parallel with 15 plus 24 equal to 24, and voltage that we will see across capacitor is going to be voltage across this 24 ohm. So the voltage that we will see initially across capacitor is going to be 16 volts. So we need this information so that when we try to find out the expression for the voltage, these will act as the initial condition, and it will allow us to find out the unknown constants appearing in the expression for the voltage. So once we have found out the voltage uh, and the switch is opened, we see that the equivalent scenario for the given circuit becomes this, which is a series combination of capacitor, inductor, and resistor. So resistor now is going to be a series of 6 ohm and 24 ohm, which is itself parallel of 60 and series of 15 and 24, so 25. So this circuit gets reduced to a simple series RLC circuit with no external source and with some initial condition. That means certain amount of energy in the system. So to find out whether this decay of the energy or the voltage across capacitor will be of type of critically damped, overdamped, or underdamped, we need to find out the quantities alpha and omega and then compare them to decide what is the case for this scenario. So here we try to find out the alpha. So we find that alpha is equal to 5 and omega is equal to 3. So in this case, we have alpha greater than omega naught. So this amounts to overdamped case. That means decay will take place completely without any oscillation. That means capacitor will not be able to get charge in the other direction. So for this case, we now need to find out what will be the S parameter. So in this case, there will be two distinct values of S, which turns out to be -9 and -1. So for this case, we know that standard expression for the voltage is going to be of this form, a constant into e raised power st. So one of the s is -1 plus another constant multiplied by e raised for the other s into t, which is minus 9 into t. So now we have two unknowns, a and b, to be determined. So once we know the value of a and b, the expression for voltage across capacitor will be known completely. So now can you find out what will be the value of a and b? What I was pointing out that we have these two unknowns. So we need two equations to solve for a and b. So the first equation becomes the voltage across the capacitor is T is equal to 0, or you can say T is equal to 0 minus or T is equal to 0 plus, because voltage across capacitor is not going to change suddenly. It is what is called continuous. That means it changes gradually. So voltage at 0 moment will give rise to one equation, and second equation can be found out with the help of current through the capacitor. Again at the t is equal to 0 moment, and t is equal to 0 moment is the moment when switch is open. So before the switch is open, current through capacitor was 0. So when the switch is open, right at that moment also the current is going to be 0 or very, very small. So initial current through capacitor is going to be 0. That will give rise to second equation. So we set up these two equations and solve for a and b, and a turns out to be 18 and b is minus 2. So we can find out the voltage across capacitor will vary as per this expression, which has two exponential terms. Okay, so here we have second problem uh, where we again have RLC circuit, and then now we have two sources, but out of that this 50 volts is always present, but there is a current source on extreme left here, and this source uh, you can see is written in the form of 2 into ut, and as you know, ut is a unit step function. That means ut is equal to 0 for t less than 0, and ut is equal to 1 when t is greater equal to 0. So at t is equal to 0 moment, this current source will come into existence, and it will also start having influence on the circuit. So our goal is to find out the voltage across capacitor and voltage across the inductor when this current source comes into existence. That means at what is called 0 plus moment. So try to find out these two quantities.
Across across capacitor, it is coming out to be 40 volt.
Yes, that is correct. So are you able to see the video?
Yes, sir.
Yes, sir, yes.
So this is x-axis, this is y, and ut is a function called unit step function. That means it is 0 up to t is equal to 0. This x-axis is basically time, and then it assumes a value equal to 1 for t greater than 0. So if we want something to come into existence only for t 0 and greater than, then we multiply that quantity with ut, a unit step function, to do this thing mathematically. So you can say that this scenario would have been equivalent to the same circuit with this condition, that there is a switch and the switch is closed at t is equal to 0, and then you have rest of the circuit here. So what has been given in the PDF file is equivalent to this interpretation. It is closed at t is equal to 0. To solve this problem, we will have to take the help of two facts. First fact is that voltage across capacitor.
Sir, is VL 80?
Yes, voltage across inductor is going to be 80 volt.
Okay.
So as I was saying that we will have to take the help of two facts. One is voltage across capacitor cannot change suddenly. That means whatever voltage was there at T0 minus, same voltage will exist at T0 plus as well. Second fact is going to be the current through the inductor. So whatever current exists at 0 minus, same current will exist at 0 plus. That means when the current source, 2 ampere current source come into the circuit existence, the voltage across capacitor is going to be same, current through inductor is also going to be same. And of course, we will have to take the help of few KCL and KVL also to set up the equation. Okay, so at before t is equal to 0, that means at t0 minus, the circuit will look like this. That means current source is short circuited, there is no current here. And then we have this 50 ohm, 50 volt on the right hand side, and then this 40 and 10 ohm resistor, and then inductor. So inductor is in fact will be acting like a short circuit because there will be constant current flowing through it. Capacitor would have charged fully and it would act like open circuit. So from here you can see that the voltage across capacitor is going to be same as the voltage across 40 ohm resistor. So we find out what is the voltage across 40 ohm resistor at t is equal to 0 minus. That means before the current source becomes active, and it turns out to be 40 volt. So voltage across capacitor is 40 volt before the current source comes into picture. And since the voltage across capacitor is what is called continuous, that means it changes very gradually. So as soon as the current source comes into existence, that means at 0 plus moment also the voltage is going to be same. That means it is equal to 40 volt. Now we will have to find out the current through inductor, because this we will be using later on. This is not required as per the question directly. So at 0 minus, the current through inductor is going to be current through this 40 ohm or 10 ohm, and they are in series. So the net current flowing through this circuit is equal to 50 divided by 50, that means 1 ampere. So this is the current through inductor. That means when current source comes into existence, then also at 0 plus, the current through inductor is going to be 1 ampere. Now our objective is going to be find out what is going to be the voltage across the inductor. So what we will do, we will first try to find out what is the current, new current through this 40 ohm. So earlier 1 ampere was flowing from right hand side to left hand side in this direction before this current source came into existence. So now this current source has been established, brought into the circuit. So we need to know what is going to be the current through this 40 ohm. So for that we write KCL at this node A. So this 2 ampere is equal to the current through inductor, new current, plus the new current through 40 ohm. And as we know, the current through this inductor is going to be same as the previous scenario. That means at moment 0 minus, which was 1 ampere. So the equation becomes 2 ampere is equal to 1 ampere plus I1. So now we have a current of 1 ampere through 40 ohm, but now it is flowing in this direction, that is from left to right. Earlier it was right to left. Okay. So what happens here is, let us try to interpret what is happening physically now. So this current source, it starts pumping 2 ampere current into the circuit. Now since the current through inductor has to be 1 ampere, so inductor continues to allow only 1 ampere current to flow through it, and with the same direction. It neither changes the direction nor the magnitude. So what happens now, there is a net 2 ampere current, initially 2 ampere current flowing from left to right because of the 2 ampere current source, and there was already 1 ampere current flowing through 40 ohm because of the 50 volt source that existed from the very beginning. So here, so now you can see that there is a net current of 1 ampere flowing from left to right, and this is what the KCL has revealed, right? So now we have 1 ampere current, net current flowing through 40 ohm and 10 ohm, and then this 50 volt, and it again comes back here with a 2 ampere. So now our objective is to actually find out what is the voltage across the inductor. That is the final objective. So for that, we try to set up a KVL in this mesh 1. So which include the inductor, 40 ohm, and the capacitor. So we write this KVL minus VL 0 plus 40 into I1 plus VC plus is equal to 0. So this VL 0 plus required voltage becomes 40 into I1, which is 40 into 1 plus VC 0 plus, which is also 40. So across the inductor now 80 volt voltage exists. So voltage across capacitor remains 40 volt, but inductor voltage changes to 80 volt from 0 volt. And this is also, you can see, in a way required because now we have higher voltage here across inductor, so that current flows from node A to the other end of the inductor. Right. So now I will share the third problem, which we will not be able to solve, but I will show it to you. So here you can see that we again have RLC circuit, but now they are sort of connected in parallel. So in this circuit, this switch is closed at t is equal to 0, and we are interested in finding out the voltage across the capacitor at certain moment after t is equal to 0. So here you can see that this source, 3 ampere source, is going to be present in the circuit. It was before t is equal to 0, and this is going to be also present after t is equal to 0. So this is a circuit with source, and here you can see that when the switch is closed, the voltage across this 10 ohm resistor is going to be 0. That means any current which was earlier flowing through 10 ohm will start flowing through this switch, and there will be no current through 10 ohm. So it is as good as removing this 10 ohm and directly connecting the two ends of this 10 ohm with the wire, which is in the form of switch. So this phenomena is called short circuiting 10 ohm. So once this 10 ohm is short circuited, we have a very simple circuit with RLC, all the three in parallel, and there is a source. So this circuit gets reduced to parallel RLC circuit with a source scenario. So this is a standard circuit, and you just need to find out the alpha omega that will determine which of the three cases it falls into, and then use the standard solution for these three cases. And then of course you will have to find out the initial conditions so that you can determine the unknowns appearing in that standard solution. So here all effort is going to be in form of determining initially alpha and omega and finding out the suitable case out of those three possibilities, and then finally setting up two equations for the two unknowns appearing in the solution, that is the voltage for the capacitor.